What?
Were you in the lounge this morning?
Yeah! Remember you was just like, you woke up and you got that little wake up hair and you was just like, what? And then we talked about,
What did we talk about?
oh, remember you was like, would you rather,
No,
change
you
genders?
asked that.
Yeah,
I
I
didn't
said,
ask
would
that.
you rather change genders every time you sneeze? Or not know the difference between a
Stupid
muffin and
question
a baby? The juniors were talking about that, so.
No, they weren't. He brought it up.
Yeah.
No, okay, so.
That's
No, he did.
one is more probable than the other.
Is that?
Would you rather change genders every time you sneeze, or not know the difference between a baby?
No, because they have to.
Oh, you gotta have a piece of that muffin?
Or you accidentally eat a baby. Yes.
If you don't like muffins, you're good. If you like muffins,
If you like muffins.
Everyone was talking about how he wanted to play with his boobs. And one of the juniors was like, and we would probably catch him.
Or like, you know what I'm good is like little packs of mini muffins.
Oh, yeah.
It's like 4 by 5.
Depends on whether you're attracted to
A guy or a pretty girl or a bakery.
like when I have
Well, you're eating your breakfast. I can't answer that.
This is a muffin. Why is the muffin crying? I don't know what's muffin is so good. What is this feel inside this muffin?
Look for the record sneezing.
Yeah. Okay. What is this muffin again? I chose the baby.
Or I chose like.
Because I'm not sneezing odd number of times. If I sneeze odd number of times, I'm gone. You won't see me in a week. I'll be
You can explain that.
Okay. I have a demo for you today. This is a little unusual. It has nothing to do with simple harmonic oscillators. I just brought it.
You just feel like having fun?
This one, yeah, this is just for fun. And I can really only do it once, so I have to try to get it right the first time, because it takes a couple of minutes to get this thing coiled back in here. And I don't want to use class time unless somebody wants to volunteer to do it, to give me another shot at it. So what you have, this is just a beaded string, like the strings on a bead, beaker. And it should be put in here so that the string can feed out easily at the top without having to pull something from on top of it. So you don't want the string to go down to the bottom and then back up again. So you want it layered. And then if I do it correctly, really I need a little ladder would be good, because the higher you stand, apparently, having done this a few times, the higher you stand, the more pronounced is the effect. So what I'm going to pull on this and jerk it down. So I'm going to get this thing flowing from the beaker down. And if I do it right, you'll notice that I'm telling you what you're going to see, right? Because it doesn't always work. What I want to have happen is for this string, it will clear the edge of the beaker. It won't drag down on the edge of the beaker. It will actually clear the beaker by inches. It's really rather amazing when you see it happen, if I can get it to work right. It isn't real stable, though, and so it is possible that it won't work when I try it. But I'm going to give it a try here, okay? I'll let you load it up again.
I don't know what they've seen that happen or hearing something.
Yeah, the audience reaction is
that red, white, and blue swag. Oh!
Okay. I appreciate the audience enthusiasm. I still haven't figured out quite why it does that, but maybe somebody here will spend some time trying to figure it out. But you can find this on YouTube. Somebody's got a nicer demonstration where it really does consistently go over for quite some time.
My question is, how does someone figure out how to do that?
Yeah, I know. And it doesn't seem to have anything to do with the stiffness of the string. That was my first reaction, was that it was a stiff string, and that's why it was arcing like that. Now, this is very flexible, right? It has nothing to do with the stiffness.
So they just plain follow the leader.
Yeah, it's in a sense, it's not a real good analogy, but it's analogous to siphoning, right? Where you get a hose, you get water in a hose going down. Of course, will suck out the entire beaker. That's why it empties, of course. But that arc is interesting. Anyway, kind of neat. Don't have a great explanation for it yet. I'll work on it. Comet Ison is coming in about a month. Nobody knows how bright it's going to be. The hopes are that it will be quite bright. It's a sun grazer, so it's going quite close to the sun. Right now, I think it's on the far side of the sun, and as it comes out, it should become visible, and or something like that. I'm not quite sure exactly. I haven't paid a lot of attention to it, but it is potentially something that you will see quite easily with the unaided eye. So in about a month, we'll be, and I don't know whether it will be in the morning or the evening. It'd be nice if it's in the evening, make it easier to see. Anyway, that looks like it'll be fun.
What is that, like an asteroid?
It's a comet is typically just a frozen mass with dirt and debris contained in it, and it evaporates off, sublimes probably, and the tail is just the stuff that's coming off of the comet. They're not very large usually. Well, yeah. So some people confuse shooting stars. Will say a shooting star is a meteor, right? Which is a different thing, right? A comet will be stationary. It won't. From one night to the next, you'll see it maybe move a little bit. And a really nice comet will have a big tail that you can see that will be several diameters of the moon in the sky. And the last one I remember was about 16 years ago, and it was really nice. It was nice, visible in the evening. Nice big tail, very easy to see. It's cool. That will actually be appropriate when we get to the chapter on gravitation, because we'll study orbits around the sun, and comets have typical orbits around the sun. Yes?
Theoretically, if any interesting event like that or an eclipse were to happen during our class, would we be allowed to go outside? And
No, I don't answer for any reason.
The class was so happy to be outside that day. like the legit class.
We'll see. We'll see. If it's the event of the year, maybe not.
Like Patrick said,
event of the decade, event of the century, I guess. Okay, so we have an exam on Halloween, 7 p.m. in Kynard 101. That's the big auditorium on the first floor, Kynard, not the ground floor, the first floor, where the undergraduate student lounge is for the physics majors. You know where that is?
I think it's where we had our test last time.
Pardon?
It's where we had our test last
Was it? I thought maybe it was in the ground floor. It was in Kynard 101? Okay.
Yeah.
All right. So same place. Now I have a question for you. The official time slot is 7 to 8 o'clock, which is all that you signed up for when you registered for this class. Is there any problem with extending the time, say to 8:30? Is there somebody who has to leave like at 8 o'clock?
I have to go back to work.
Okay. Go back to work. That just
Like
short-circuited.
I'll be at work at 8 o'clock in the morning, and I'm leaving at 5 to be here at 7, and then I go back afterwards.
That just short-circuited my other possibility. Was that you could start early, say 6:30 to 8. Does that create a problem for you?
I'll figure it out.
I don't want to put a
It's
torch
all right.
on
Starting early.
I'll just be really late.
We start early too.
It's all right.
Well, yeah, I could give you one of two choices: start at 6:30 and end at 8, or start at 7:30 and end at 8:30. Okay. In other words, an hour and a half. I don't want to have a lot of variations. 2 is about as much as I want to try to handle. But if that creates a problem for you, we'll work out something. Okay. I don't want to make it hard on you. I want to make it give you more time, right? I mean, we don't have that. We got 50 minutes here. We have an hour there. We could even do an hour and a half, and then there's less crunch. You can spend more time working through stuff. So tentatively 7 to 8:30. If somebody really wants to start at 6:30 and work to 8, let me know, because I could arrange to come there early. You want to do that? Okay. How many think they would do that? Start at 6:30. Or 6:30
to 8.
No, I'm not going to do that. 6:30 to 8.
AM to PM?
PM. All times are PM.
That's awesome. That would help you out.
Skip all your classes.
Okay, so I'll give you a choice. That you can start at 6:30 and end at 8. We'll start one group at 6:30. Come a couple minutes before 6:30. We'll seat those people in the same room, seat them, get them started, and I'll pick up their papers at 8. Another group will start at 7. So if you missed the 6:30, you'll start at 7. Be done by 8:30. Okay. I don't want to get more than an hour and a half, but that gives some variation. And if that doesn't work for somebody, let me know, and we'll work out something. Okay. Give a little bit more time. And there are a couple of people missing, so I need to keep track of Ms. Maw and Mr. Hodgkiss to talk to about this. Okay, now a related thing is on the last test. The test on chapters 1 through 4 did have a confusing set of instructions, which is my fault, mea culpa. It's not something that, actually I've given that test, almost the same test, for like 5 years and haven't had that problem before, but it's quite reasonable to be confused. I can read the instructions and see that they were confusing. So here's my offer. Here's my resolution. I will calculate your final grade, that is for the term, one of two ways. Calculated with the test on chapters 1 through 4, the one we just took. You have your grade on that. Or without.
Oh no.
And I will take the better grade that results, the better final grade. In other words, whatever's in your favor. Because there were some people who did fine on that test, and I don't want to discount the test. They would probably very much like to have the results of that test included in their final grades. So I'm going to figure out which way is to your advantage. For those of you who could reasonably claim that it really confused you, then you can drop it. Right? In effect, we'll drop that from your scores. Okay?
What if it was a different question?
What's that?
What if it was a different question?
There are lots of possibilities, and I can't cover all of the bases, but I felt this was a fair resolution for those who did fine on the test, and then for those who reasonably got confused.
Oh, so this works for
You're
everyone?
taking,
Everyone.
You're taking the best final grade. That's fabulous.
Yeah. You don't even have to. You don't even have to choose. It will be done for you in your favor.
Wait, so that means we're both
Hey, don't worry about
or
it.
you
This-
don't do 1 through 4?
This last test, only this last test, the one that I gave that you took in class on Monday of last week, a week ago, right? It was a week
You
ago.
got like 85 on it.
That's not good enough.
Well, then.
He gave it.
Are our
Helps your grade.
in-class tests as weighted as the
Got you, Gary.
departmental tests?
Yes, all of the chapter tests are weighted the same. Right, and they're combined with a homework grade, I think. In the syllabus, it says combined with the homework. I can't remember precisely what it says in the syllabus, but it's spelled out in the syllabus. Okay, so all of these chapter tests are weighted the same. Chapter 1 test, all of them. This next test coming up, they all have the same weight. Of course, the difficulty increases with every test. They get harder.
So what does the quiz count as?
Yeah, the quiz I counted as 3 homeworks.
Oh, thank you. Whew. Okay.
Okay, so it's included in the homework grade and it counts as 3 homeworks. Okay, so let's go on to, if you have any questions, you got any difficulties with this, see me afterwards if you like. I'm happy to discuss it, but it seemed like a fair resolution to me. Okay, the chapter 6 is on a new kind of motion, or a kind of motion that we haven't considered yet. So we have considered previously two kinds of motion, generally speaking. Would somebody like to tell me? Mr. Kelly. Pardon?
Uniform linear translation.
Alt and ULA. Yeah, uniform linear translation, uniform linear acceleration. Now we're going to consider a case which is neither of these. It's in a different class by itself, different category by itself. Uniform linear translation occurs when there are no forces. Uniform linear acceleration occurs when there is a constant net force or constant forces at work present in the system. Gravity, kinetic friction as long as the surface doesn't change, tension in the rope as long as something doesn't happen, and you cut the rope or something, right? These sorts of things, situations we've done before. We get constant force produces the same acceleration over time, uniform linear acceleration. The equation of motion, Newton's law, a typical one, for example, for uniform linear translation is mx double out of 0, and so x of t is x naught plus v naught t. For constant forces, we may have a case, for example, gravity. Let's suppose we use y. And then we have y of t is equal to y naught plus v naught minus 1/2 gt squared. So we have a quadratic. We have a linear function in time and a quadratic function in time. Now we're going to do the simple harmonic oscillator, which is a really prevalent example. This occurs throughout physics. The simple harmonic oscillator is everywhere. And part of the reason is because we can solve it. It's one of the few things we can really solve easily. But the other reason is that there are a lot of physical systems where you get something that's either is simple harmonic motion or really close to it. And so we will consider in this chapter both simple harmonic motion and damped harmonic oscillators. So simple harmonic oscillator and a damped harmonic oscillator. We're going to do both of those in this chapter. Primarily the simple harmonic oscillator, but the damped oscillator is important as well, because most physical systems are really damped. There's some damping that's present. Okay, so let's consider the case of the simple harmonic oscillator. And let's suppose that somebody would like to give me a physical system that's a simple harmonic oscillator, an example of a simple harmonic oscillator. Mr. Avery.
A metronome.
A metronome. Okay. A pendulum. Let's invert it. A metronome has a spring, so it's a combination of things. How about a pendulum? Is that a simple harmonic oscillator? A pendulum.
If you're not having certain damping effects, like.
Okay, if we take away damping, is it a simple harmonic oscillator?
Yeah.
Yes.
No, it's not. It's close, but it's not. It's periodic. It will keep returning, and if it's not damped, it will oscillate. But if you look at the angle, say, as a function of time, in general, it's not a simple harmonic oscillator. Now, it's approximately a simple harmonic oscillator if the angle of motion, if the amplitude of motion as the angle is really small. That is, a small angle to the pendulum is very close to a simple harmonic oscillator. Now, we'll go back and do this in the next chapter, in chapter 7. When we do rotating bodies, we'll do the pendulum. So you'll see how it is that this is not a simple harmonic oscillator. It's periodic, but it isn't harmonic. Kind of interesting. So let's put that one on hold for a minute. How about another one? Anybody else have a, Mr. Flanagan?
Simple circular motion.
Simple circular motion. Yeah, okay. How about, yes, in a way, there is that relation, there is that, certainly that resemblance, but it involves two dimensions, right? It involves motion in two dimensions to have circular motion. So how about something that involves motion only in one degree of freedom? The pendulum only swings back and forth, so that's one-dimensional in that sense. The spring, a mass on the spring is what I'm looking for. So we could hang it from the ceiling, which adds gravity to the problem, or we could put it on a table. Okay, now the characteristic of a spring that we're going to use is that it pulls the mass back to, pulls or pushes the mass back to some equilibrium point. So there's a characteristic equilibrium length of the spring, which say I'll call L naught. So here's a wall, and here's a mass. And now if I pull that spring, I stretch it a distance x from equilibrium. So x is measured relative to that point of equilibrium. If I put the mass attached to the spring, I put it at the equilibrium point, there's no force acting on it, because the spring is neither stretched nor compressed. So it's at equilibrium. So it's called the equilibrium point, or equilibrium length. If I stretch, then the mass, the spring will pull. It's in tension and will pull. So the mass will then experience a force that pulls it back. And the more I stretch, the bigger the restoring force gets. So the restoring force is proportional to the stretch. F is negative kx. Negative because it's in the opposite direction. It wants to restore it back to 0. So the force is in the opposite direction to the stretch. If I compress the spring, so if I have scrunched the spring here and I push the mass in closer than its equilibrium distance, in this case x is negative, right? So the force in this case, again, is negative kx, but it will be positive. And in this case it's negative, in the sense that x positive, I've chosen x positive this way. So positive x is to the right. So in that case, the force is always negative kx. What's the name for that force law? Hooke's law. So anytime that you have a force which is restoring and which is proportional to the displacement, you will have simple harmonic motion. Yes, ma'am?
So cardiac fibers in the heart, they follow Stirling's law, which does the same. It's the same concept.
Okay.
So the heart then is simple harmonic motion. They actually calculated it. Physicists did it. They calculated to see whether or not they could tell the arterial pressure if it was going to be the calculated value was going to be different than the actual value, and it's close.
So in that case, there.
There's the spring concept.
Yeah, that's right. So there's the stretchiness of the membrane.
Mm-hmm.
But the membrane itself has the ability to contract, right? So it's there's
Yes,
a couple
but
of
it's directly
things.
proportional. The more that you stretch it, the harder it
Right.
contracts.
It's yeah, right. So not a simple system, especially to put on a table to use. So I won't take any volunteers for that one.
I'll bring a patient in.
No. Okay, but there are lots and lots of cases where Hooke's law holds. The pendulum, you might think, well, there's one, right? Because I pull the pendulum over and I let go, and there's a restoring force. But notice, if I keep pulling the pendulum, the restoring force actually decreases. It doesn't increase linearly with increasing angle. Because, in fact, if I pull it all the way over, it reaches a almost zero value. The restoring force right at the top will be 0. So the restoring force is actually decreasing. It's not increasing at the same rate that Hooke's law.
Could that be shown with its shadow?
Shadow?
Where the point where when you pull up, where it's like shadow would go back?
You mean projection down onto the x-axis?
Yeah.
No, it doesn't work, even in that case.
No, I'm saying like the point where the shadow would turn back around, is that where the restoring force would lessen?
Sure, yes, that's right. It depends on the projection in the x direction, but the restoring force is not proportional to that, okay, even for the pendulum. We'll see how that works out. It's a trig function for the pendulum. The restoring force is proportional to the sine of the angle. Not proportional to the angle, but proportional to the sine of the angle. Okay, and then we'll see it's not, strictly speaking, simple harmonic motion. It is periodic, but not simple harmonic oscillator. Okay, now gravity, hanging this thing on this from a ceiling like that, where we have gravity acting on it, actually doesn't change the motion. All it does is stretch the mass. It shifts the equilibrium point downward, but then you still get oscillatory motion around that new equilibrium point. And we'll work this out. This is one of your homework problems to demonstrate that it's still actually simple harmonic motion, just the spring is a little bit longer because of the weight of the mass, because of gravity. So that's simple harmonic motion as well. Now, hold on a second. What can go wrong here? A couple of things. You can pull the spring too far, and it won't come back. You can plastically deform the spring. Okay, that certainly is not Hooke's law. You've gone beyond Hooke's law. Another thing that can happen is that the spring, while not permanently deformed, actually can't provide as much restoring force, or provides more than enough restoring force. In other words, it's less than linear or beyond linear in the force. Okay, so those are again, rule out. They're not called simple harmonic motion. That would be something that goes beyond that. So simple harmonic motion is strictly limited to the case where Hooke's law is going to be good enough to describe the motion. That is, any deviations from Hooke's law are so small that we don't have to consider them. Okay. So lots of physical examples. When we get to the next chapter, next semester, we're going to do an RC circuit. You have a capacitor. I'm sorry, not an RC circuit. An inductor, an LC circuit. And you could put charge on the capacitor and then let it go, and the charge will flow through the inductor and then charge up the capacitor on the other side. So the charge goes back and forth. It goes from plus minus to minus plus, back to plus minus, oscillates. And in an ideal circuit, this is an example of a simple harmonic oscillator. You can make a clock out of this, an LC circuit. Just flows back and forth, back and forth, back and forth. Okay. Lots of examples of simple harmonic motion. A string on a guitar. If you've got it in one mode, executes something that's very close to simple harmonic motion, like this. So if you get a rubber band stretched between endpoints like this and get it oscillating back and forth, that's an example of something that's like simple harmonic motion. As long as the amplitude's not so big, not too small. Well, too small is okay, but not too big. Okay, lots of places where we see simple harmonic motion. Now, another thing that's important is the damped harmonic oscillator. So the simple harmonic oscillator, the equation of motion for the simple harmonic oscillator for Hooke's law is just this. And for the LC circuit is that. So you have the second derivative of the variable, and you've got the variable again on the right-hand side. So the force is dependent on the magnitude of the displacement or the charge or whatever is present. So Mr. Avert had a question first. Did I answer your question, or you forgot it?
With the masses, with the spring.
Yeah.
Does it matter the mass of the spring? Or?
We'll find out here. Okay.
Yeah, with K,
Yes.
what are the factors that influence what that is?
Yeah. So K is called the spring constant, and it depends on the material and the geometry of the spring. So how many turns, how stiff the material is. Even just a straight wire has a spring constant. It's really stiff. It's hard to pull a straight wire. It's hard to lengthen it. But you can get a little bit of stretch out of it. So it's got a very high spring constant in that case. If you coil it to make like a shock absorber or a spring, then the material itself can still be very stiff, but the geometry allows it because the spring itself is distorting, it's changing, taking some of the flex. So even though the material has a high spring constant, the spring itself may have a lower spring constant. So you can take a high strength material with high modulus, high spring constant, and change its geometry and make something spring out of it. Okay, so you can modify this in a lot of different ways. In the case of the LC circuit, we'll see this is the inductance and the capacitance. So if you don't know what those are, it's not going to help you very much, except I'm going to keep pointing out as we go along. There's another simple harmonic oscillator. There's another simple harmonic oscillator. It's all over the place. Okay, and you'll see them continuously through graduate school if you go into it. Okay, so before we start studying the simple harmonic oscillator, I want to point out the damped harmonic oscillator. So this is the simple harmonic oscillator. The damped harmonic oscillator, I'm simply going to write an equation for you. And we'll come back and study this some, but just for now I want to kind of write it down. So in addition to the spring, I have something that's resisting, causing resistance in the motion. So do you remember this term that we talked about back in chapter 4? We discussed kinds of forces, and I mentioned one almost in passing. You did a little bit of work on it, not a lot, where the drag force is proportional to the speed. What was the physical case where that's present? Air drag, water drag, flowing through a fluid. Not perfect, but it's not bad. So here's an example. Let's suppose we just consider that there's an addition to the spring, there's air resistance or some kind of fluid resistance. And that will clearly dissipate energy from the system. In fact, if you had a simple harmonic oscillator, you stick it in a liquid bath and you let it go, what do you expect to have happen to the temperature of the liquid? An increase. So that's another example where the friction is showing up as heat. Motion, mechanical motion is showing up as heat in the liquid. So we did that when we considered inelastic collisions. So we keep touching on heat, and we will come back to the connection between mechanical energy and heat when we study thermodynamics in the next semester. Okay, so all these jumping off points that I'm just announcing, and we're going to go on. Okay, we'll come back and see them later. Okay, another circuit which also has an analogy to this is to recognize that not all circuits are have no resistance, so we include a resistor. So we have an LRC circuit. Same differential equation again. Second order. It has an additional term, the resistor here. What happens when you pass current through a resistor? Like a light bulb. It heats, right? Gets hot, gives off light. Pass enough current through there, you'll definitely see it. So the resistor is like the air resistance in this analogy with a mass on a spring. Okay, so now we have these two cases that we're going to study. We want to be able to understand the differential equation and the nature of the motion that we get. In the case of the simple harmonic oscillator, do we have, let's go back to the simple harmonic oscillator. Let's go back to this one. Let's forget the resistance and the drag for a moment. We have simply mass on a spring. So I use the same symbol both for an inductor and a spring, which could cause some confusion. So that's a spring with a spring constant and a mass. And we have this equation of motion. Now let's, before we get into a discussion of the equation, let's go back and look at, kind of understand what we expect to see happen. So I would like a volunteer, please, to go through this following problem. In terms of the impetus and force, explain the motion that you would expect to see if I take that setup with a mass on a spring on a table, and I pull the spring out, hold on to the mass, and then let go. So I want somebody to walk through what happens. I mean, you all know what happens. It does this, right? But I want it in terms of impetus and force and mass. I'll let Mr. Destin try.
So you have it pulled out,
Yep.
and that is the force. The spring is exerting the maximum force of that particular experiment when it's pulled all the way out.
Good.
And then you let go, and when the force of your hand goes away, then the force adds impetus to the block towards the equilibrium point.
Does it start off with any impetus?
No.
If I stretch it, hold it there, and then let go, it has no initial impetus, right?
No.
The spring is now pulling it back towards equilibrium. Gives it impetus. Keep going.
And so the impetus of the block increases until it reaches an equilibrium point, although the rate at which this impetus slowly decreases.
And why? Why is that?
Because the displacement decreases as it moves towards equilibrium.
The spring is less and less stretched. As it gets back to equilibrium, the force that the spring is exerting on the mass is diminishing. So this is not uniform linear acceleration anymore, right? Okay, then it reaches that equilibrium point. What happens there?
Then its impetus reaches a maximum because at that point the force is zero.
Yeah.
And then the force moves to acting against the motion of the block. So it loses positive impetus / gains negative impetus.
Yeah.
And as it
actually loses positive impetus, yeah. So it overshoots, right? It goes past that point of equilibrium when the force has stopped acting on it, but it overshoots because of this impetus. And then
as it continues going on, displacing more, then the rate at which it loses impetus increases.
Right.
until finally it reaches the displacement on the other side, maximum displacement,
Right.
and it once again has zero impetus,
Right.
and then it starts again.
And it just goes back in the opposite, kind of a mirror image of what it did the first part. So there's two parts of the motion, this way and then back again. It comes back to where it starts from. So notice on the inbound leg, the force is pulling it back to equilibrium and the displacement is back to equilibrium. What's happening to the kinetic energy? Increasing. The work energy theorem tells you force and displacement are in the same direction. It's going to be gaining kinetic energy. Now it gets to that point equilibrium where the force vanishes, but it overshoots. And then a little bit of force starts building up back in the opposite direction. Now the force is opposing the motion. What happens to the kinetic energy? Decreases. Right. It's becoming potential energy. Yeah. So we're going to come back to that question about potential energy. And so that is what I'm looking for with the connection between impetus, force, and mass. When I ask for principal explanation of the oscillation, simple harmonic oscillator. It's very important to recognize that the force is proportional to the displacement, Hooke's law, for the simple harmonic oscillator. Okay. All right, very good. That's what I wanted. Okay, now, so we expect to see some kind of oscillatory behavior here. This is a second-order differential equation, so we can establish, say, some initial conditions. Like, for example, let's suppose I stretch a displacement A from equilibrium, start it from rest, let go. Okay, so I have a differential equation and two initial conditions. This is what we've done before. But you can't solve this equation with the polynomial solutions we've tried before. You can include any number of terms in a polynomial, and it won't solve this differential equation. So we had a linear function, then a quadratic function, and you might be tempted to try a cubic function. It isn't going to work. Let's try a cubic function just to demonstrate. So, just for example, just to show, let's take the derivative. The second derivative. Okay, and now let's substitute this onto both sides. I want the x double dot over here with the mass on the left, and then the x on the right. But you'll see that you have terms involving t cubed on the right and no associated t cubed terms on the left. So there's no solution of this form. It just isn't going to work, not for all times. Okay. So what you should be able to do, you don't have at this point, probably, some of you might, but most of you, I'm not assuming that you do, the mathematical muscle to solve a differential equation like this. You have an entire course coming up on the subject of differential equations. How do you solve these things? So that's in the future for you. So for now, I'm going to give you a solution, and this you're going to do with homework, is to demonstrate that a solution, for example, like this, matches the initial conditions and satisfies the differential equation. So you can use the substitution, the direct substitution method, to do this. And so let's try that. X dot is minus omega A sine omega t, and x double dot is minus omega squared A cos omega t. And so if I put this into the Newton's equation, the left-hand side, which is mx double dot, looks like that, and the right-hand side, which is minus kx, looks like that. And so the cos omega t matches on both sides. So as a function of time, the left-hand side and the right-hand sides can be the same for all time, provided that the coefficients in front are the same. In other words, this has to equal this. And notice that the amplitude drops out. The amplitude occurs in both sides. So what I have is this relationship that k over m, let me write it this way, I have to have that omega is square root of k over m.
How did you get the negative ka cosine?
That's negative kx, right? If I go back to my differential equation here, mx double dot is equal to minus kx.
Yeah, x is okay.
I substitute x double dot, which is minus omega squared a times the cosine, and the negative kx. So I have a negative sign on both sides. cosine on both sides, A on both sides. So then I have to have that omega has to have this relationship. It has to be the square root of k over m. So omega, then, looking at this, this is a simple harmonic motion, and this is what we mean by simple harmonic motion, is it's a cosine like this, and it just goes forever in time. The period of motion is 2 pi over omega. That's the period, that's the time it takes for it to make one complete cycle. And the amplitude is A. It goes from plus A to minus A. And it never stops. If there's no resistance, if there's no air resistance, if there's nothing that dampens the motion, it will do this forever. So to the extent that this differential equation describes what is really present, there's nothing that will slow it down, make it stop. Mr. Kelly.
Were they mentioning the phase angle phi?
Yeah,
Basically,
the first thing, let's get there. Hold on. Let's take these steps one at a time. Okay, so the first thing to notice here, was A determined? How is A determined?
How far stretch it out?
Right, yes, sir. By the initial condition. So let's look at x of 0. X of 0 is A times cosine of 0, which is, cosine of 0 is 1. So x of 0 is just A. That's the initial stretch. And x dot of 0 is minus omega A sine omega t. And we said that we started off from rest, so that's good. That matches the initial conditions. Okay. So A is determined by how much you stretch it. But the frequency is not determined by how much you stretch it. The frequency of motion, omega, is determined by the stiffness of the spring and the mass that you hang on it. So if I take two simple harmonic oscillators and I stretch one that far, and I take another one and I stretch it twice as far, and I let them go, which one gets back to the original point sooner?
First one.
It doesn't affect the frequency.
Same time. Doesn't affect the period. The amplitude doesn't come in to the period. It doesn't affect it. They come back at the same time.
Because there's less force when it's closer to equilibrium anyway, so
Right.
the more force is limit there, we bring it back fast.
So the same spring, you stretch it out far, they won't affect the frequency?
It does not affect the frequency of motion. As long as we're talking about Hooke's law. If we're not doing Hooke's law, you can't say this anymore. And the pendulum is an example where Hooke's law does not hold, and the period of motion of a pendulum does depend on the amplitude of motion, as we will see. Okay? But for Hooke's law, for a simple harmonic oscillator, the period of motion doesn't depend on the amount of stretch that you give the spring. It depends only on the stiffness of the spring and the mass. Now, if somehow the system is starting to show some dependence of the period on the amplitude, it's because it's not Hooke's law anymore. Something new has been added. Okay? All right, so that's a characteristic of simple harmonic motion. The amplitude doesn't affect the period. You can make it as big or as small, and it's not going to influence how long it takes to get around. So if you double the amplitude, well, the force is doubled now, right? And so it's going to it's farther to go, but it's got more force. And so it's going to make it back around in just the same amount of time. Okay, so that's simple harmonic motion. All right, now there are lots of solutions to this. There are lots of forms for this. Here's another one. Let me give you another example, x of t, which is going to involve both cosine and sine. If I try this is also a solution to the differential equation. If I had just the cosine piece, just the sine piece. Let me do that first. Let's just do the sine piece, just to demonstrate, and then we'll take the combination. So suppose I have a combination that looks like this. Let me use the sine function, b sine omega t. And let's take the derivative, minus omega b plus omega b cos omega t. X double dot is negative omega squared b sine omega t. So once again, we have the same thing. Omega still must be square root of k over m. This satisfies this differential equation. But the initial conditions, now let's look at the initial condition. X of 0 is now 0, whereas x dot of 0 is omega b, which is then the velocity. So b will have to be omega over the initial, oops, other way around, the velocity over omega. The initial velocity over omega. So in other words, this satisfies something that starts at the origin, but is given an initial velocity. So it starts off at the origin, you give it a kick, get it going. Okay, that's also simple harmonic motion. Let's draw this. Starts off with some velocity. Okay, and now we have V naught over omega to minus V naught over omega. You might want to check the dimensions here. Velocity divided by omega. What's the? I should have done that already. What's the dimensionality of omega?
Would be nothing or 1.
It's not 1. So notice that it's in the trig function omega t, and the argument of a trig function must be dimensionless. So omega has inverse time, and the period, which is 2 pi over omega, the period, how long it takes for it to swing up all the way around, 2 pi over omega, the dimensionality of the period is time, right? It's inverse omega, so the period has dimensions of time. Okay, and we should check that. Let's go back to look at K and M. Well, M is mass. Of course, it has dimensionality of mass. K, let's look at K. Kx is a force. So the dimensionality of Kx is mass times an acceleration. Kx must be a force. So what is K? If x is length. Mass over time squared. So K over M has dimensionality of inverse times squared, and so the square root of K over M has, which is omega, has inverse time. That's what a frequency is. It's an inverse time. It's also a rate. You can think of it as a rate of oscillation. The frequency corresponds to a rate, therefore an inverse time. 2 pi over omega. I go through one cycle of the trig function, right? The argument of the cosine goes from 0 to 2 pi and it starts all over again. So I go through full 2 pi and then the motion starts over again. So 2 pi over omega is the period of the motion, how long it takes to go back. Now I can take combinations of this. So if A cosine omega t corresponds to a displacement from rest, and B sine omega t corresponds to something that starts at the origin with an initial velocity, can I do any general motion by taking a superposition of the two? And it works. You'll find that out when you do the homework for Wednesday. This is a general solution. So A is then the initial displacement, and B is the initial velocity divided by the frequency, and the frequency still must be this ratio, square root of K over M. So this matches all possible initial conditions. That's the general solution for the simple harmonic oscillator. But there are other forms. He gives a different one in the book. He uses is it cosine plus delta? I can't remember now. I want to use the same. Here it is. Equation 6.4. He writes this. Equation 6.4. He writes it x of t is a sine omega t plus phi, where phi is the phase shift that Mr. Kelly was wanting to talk about here. So this phi here is a constant, and it's a phase shift. And that's because if you go back to look at the drawings that I made for the motion up here, for the cosine and the sine, here's the sine motion. Starts off with the sine on the right-hand side here, and then earlier I drew the cosine. They're just shifted from each other. It's the same kind of wave. The sine is just shifted from the cosine, and so In general, you can write, instead of a combination of cosine and sine like this, you can write it as one trig function with a shift. So phi is called a constant, it's a phase shift. It is called the phase shift, it is a constant. And A is also a constant, and that's the amplitude.
So it doesn't matter if you use sine or cosine?
Correct. Yeah, the phase shift will be different. What you call the phase shift will be different depending on whether you use sine or cosine, but either one will work as a solution. And then the frequency of the motion is omega here, also a constant. So we have three constants to describe the motion. In this case, the amplitude, the frequency, and the shift. Or we could do, as we did before, A and B and frequency. We did cosine and sine parts. Three numbers to describe the general simple harmonic oscillator, depending on how you do it. In the end, it's all the same. There's some simplicity from just dealing with one sine, or just one trig function at a time. Okay, now, is this spring a conservative or a non-conservative force? The force that the spring exerts on the mass. Let me have a hand here, and then the volunteer who hasn't tried it yet before.
Support.
Mr. Kremlin.
Conservative.
Conservative force. Why do you say that?
Because it's not decreasing. Like the force is always going to be not constant, but
Yeah, it's not constant, right? Gravity was easy because it was constant, so.
but at each point on either side, it's going to be constant. Like it's always going to apply the same amount of force at full extension.
So remember, what was the criterion for conservative force? We phrase it in terms of the work done by the spring. So there was two different ways we did it. Who remembers the criterion for conservative force from chapter 5? This could be on the test Thursday night, so it might be a really good thing to remember this. I'm gonna call on somebody who hasn't answered yet today.
Don't we get like names in a bucket?
Names in a bucket. He's volunteering her. Yeah, that's really gentlemanly. Ms. Shaven, say it out louder.
Heat and passive.
Right. So a non-conservative force generates heat. A conservative force, the work done by conservative force does, you can do it one of two ways, does not depend on the path to go from A to B, or there was a second way of saying it. If you go through a closed path, what is the total work done by a conservative force?
Doesn't depend and you end at the same spot, huh?
Yeah, it's zero. The work must be zero because it doesn't matter. You might not have gone anywhere, in which case the work is zero. Or if you've gone out this way and come back, then it must be the same result. So the work is zero. Okay, let's consider the cycle then. This mass is moving back and forth on the spring. Okay, the work done, it's positive in this case because the displacement and the force are in the same direction. So we get positive work. Now the force is opposite, negative work.
then in one oscillation, it's always going to turn to the same place.
There you go. When it comes back now, more negative work, then it goes, I'm sorry, now it's positive work because they're both going in the same direction. Now it flips again and back to negative. When it comes back around, it will have done a net zero work. The spring will have done no work through one cycle. Okay, and you can prove this is true for any motion of the spring. So it's conservative, and that means that there's a potential energy associated with it. And if the potential energy is the derivative of if the force is the derivative of the potential energy,